Alright, this video about Logger Pro is, okay, once we have all of our data in, what are we going to do with it? Okay, now the object of this class in physics is we want to find the relationships between variables, meaning if I have variables of distance versus time, I want to know as time increases what happens to the distance. Okay, we're trying to come up with, are they directly related, are they exponentially related, are they inversely related, is there absolutely no relationship whatsoever? These are the things that we're looking for. Okay, now right off the bat, if you get data that looks similar to what I have on the screen right now, meaning it basically already looks like a line. It looks like a straight line. If I double click on my graph and I put connect points and those points look like they're a straight line, then we can basically say this is already linear. If something is already linear, you're done. You don't have to do much of anything else. All you're going to have to do is go up to the top and click the R equals button, which says linear fit. And if I click on that, you're going to get a little box that has some data in it. Now, I'm going to go ahead and change the appearance of this so that you guys can read it a little bit better here. If I go ahead and blow this up, you get a little set of data here. Now, one thing I want to point out right at the top, it gives you a generic form in y equals mx plus b form. On the y-axis is d, distance. M is your slope, and the slope is given right here. T is on the x, time, down below. And b is your y-intercept, which is labeled here. Okay, so what you're going to end up with is a generic form. Now, when we go to write our equations, we were going to want to see distance equals, and then instead of m, we want to see 1.000 meters per second times time, actually write out time, plus b, which in this case is 0 meters. One other thing that we want to point out is this, the correlation. The correlation here is labeled as 1. That means that this is a perfectly straight line. I mean, if I look at my data, I just got 0, 0, 1, 1, 2, 2, 3, 3. So that it's perfect line, okay? That will very rarely, it'll never happen basically in lab. We won't ever have something that is that perfect unless, of course, you're fudging your data, okay, which I don't recommend, okay? But that's basically the idea here is once we get a linear line that's redundant, we want to actually write an equation for it in y equals mx plus b form. If it's already linear, fine, then it's perfect, okay? Another one that you might end up with, let's just go ahead and say we get data that looks like this, okay, where it's just a flat line, okay? If I do fit a line to this, you're going to notice that the slope is 0. If you ever get a slope that is 0, that means we have no relationship. Does that mean we can't write an equation? Absolutely not. We can totally write an equation, except it'll just be distance equals, the slope will be 0, so 0 times time is simply 0. So essentially this whole equation boils down to distance equals whatever b is, which in this case is 5.000 meters, meaning no matter what the time was, the distance the object was at was 5 meters from wherever we were measuring from. Okay? Just means that the object was standing still in this case. Okay? So let's say we don't have data that is perfectly linear. Okay? Just give me a second here. Let's see, we're going to make a little x squared data here. 16, 25, 36, 9. Okay. Okay, let's say we have data that looks like this. Well, this is obviously not a straight line. One way that you can prove it to yourself that it's not a straight line, if I fit a straight line, I've got a couple points that start here above my line of best fit. The majority of them are below, but then my last two are back above. If you ever have a situation where you fit a line and you find that the first two and the last two are on one side of the line and all the rest are on the other, probably means that it's not a straight line. Okay, so what do we do if it's not a straight line? Well, we're going to do what's called a calculated column. Okay, so here's what we're going to do. Identifying right away that the shape of this graph is an x squared, meaning as time increases, distance increases, but it increases exponentially. Okay, what I'm going to need to do here is I'm going to need to change time to be time squared. So if I go up to data, go down to New Calculated Column. You get a New Calculated Column box that pops up. We want to call it time squared. Now this doesn't have to be time. Whatever variables you're working with, you can do all the same things. That means my short name is going to have to be t squared. And also my units are going to have to be seconds squared. Now here's the most important part. When you get down here to the equation, we want to take pre-existing data and alter it. So what I want to do is I want to make x squared. Well, that's the time portion. So I want to take time and square it. Well, I already have a column full of time data. So as opposed to going through and manually squaring everything, that's what this calculated column's for. I'm going to select variables, time, and you'll notice that it comes up in quotation marks. And now I'm going to square that data, and I'm going to hit done. Now you're going to see that right here along the right, I'll leave my cursor there for a second, in blue along the left-hand side, I've got a set of time squared data. My graph hasn't changed at all. Why? Because I'm still graphing distance versus time. So if I click on time, I can select time squared, and now you notice that the whole entire graph has shifted to a line. It's linear now. I'm going to go up here and I'm going to type in that this is distance versus time squared. Okay. And now that it's a line, now I can go ahead and fit my actual line. Okay. And again, I'll blow this up here so you can see it. Not a whole lot's going to change from our last one because I used some pretty simple numbers. But now you're going to notice that instead of, or for our short name here, we've still got distance, m. M is now 1.000 meters per second squared. You see that the units has changed because we're not using time in seconds, we're using time in seconds squared. X is now being used for the x variable because it doesn't readily recognize t squared. So it is time squared that is there, and then the y-intercept is still 0 meters. Okay, so that's how we're going to go ahead and add calculated columns. Now, just because I feel like this is an issue, if you want to go back into your calculated column, let's say we didn't want to square time. Let's say we wanted to take the inverse of time. You would take 1 over and then select time. Oops, that's not the right one. Time. Okay, so like if we had an inverse relationship, that's what you would do. If you had a y squared, like if it would say it was distance squared, then you would select distance first and then square it. Okay, so generally we're either going to square something or invert something. So if you're going to square it, simply select the column, add a square at the end. If you're going to invert something, take 1 over. Okay, all right, so that's how we do calculated columns. Okay.